Scientists have recently proven that two particles can be perfectly linked even if they never existed at the same time. How can a particle today be synchronized with a particle from yesterday if they never met and never shared a single moment of reality? This discovery forces us to ask the title question: how did physicists time entangled photons to prove the classical story of cause and effect is wrong? By the end of this video, you will understand exactly how these measurements were taken and why they reveal a universe that does not care about our human ideas of before and after. We usually think of the world like a series of pool balls hitting each other, where one event clearly leads to the next. However, the core spark of this mystery is a strange result called entanglement swapping, where particles that have no common past behave as if they are twin souls. We know that these correlations are real because we can measure them with incredible precision, but what is unclear is how the universe maintains this connection without sending a signal faster than light. If we could find a hidden signal, we could save our old ideas, but every test shows that no such signal exists. Before we dive into the deep mechanics, consider this one small payoff. Physicists can now use a quantum switch to make a photon experience two different paths in both orders at once, meaning event A happens before event B, and event B happens before event A simultaneously. This is not a guess. It is a measurable state that we can verify in the lab today. To understand why this is so shocking, we have to look at the default story we have told ourselves for centuries. In the old model of physics, every object has fixed properties like color, position, or speed, and these properties stay the same until something touches the object. If two objects are related, it is because they started at the same place or exchanged a message. We dismiss contradictions to this model because our brains are built to see the world as a sequence of independent things moving through a fixed background of time. When we see two distant particles acting in perfect unison, our first instinct is to assume they were programmed with a set of hidden instructions at the start. We imagine they are like two identical clocks set to the same time, carrying their pre-written scripts across the room. This local realism feels safe because it keeps the universe predictable and keeps cause and effect in a straight line. But when we actually time these particles, the clocks stop making sense. The first major anchor contradiction comes from the Bell test experiments, which were designed to see if particles really do carry hidden instructions. Imagine two researchers, miles apart, who each have a detector. They receive a photon and choose how to measure it at the very last microsecond. If the photons had a pre-written script, there is a strict mathematical limit on how often their results could match. This is known as the Bell inequality. However, when physicists run these tests, the particles match more often than any classical script allows. The measurement method is key here because the researchers change their settings while the photons are already in flight. This leaves no time for a signal to travel between the two detectors, unless that signal is moving faster than light. Because we have never seen anything move faster than light, the old model of pre-written instructions fails. The particles are not following a script, they are deciding their state at the moment of measurement, regardless of the distance between them. To make this even more difficult for the old model, physicists had to close the communication loophole. In early experiments, critics argued that perhaps the detectors were close enough to whisper to each other. To fix this, researchers moved the detectors so far apart that even a beam of light could not bridge the gap in time to coordinate the results. They used high-speed random number generators to pick measurement angles at the last possible moment. The data showed the same impossible correlations. This proves that the results are not a fluke of local timing. The particles are linked in a way that ignores the physical gap between them. This forces a sense of reverence for the scale of the mystery, because it suggests that the fabric of space is not a barrier to the connection between two quantum objects. Another layer of proof comes from closing the detection loophole. For a long time, skeptics suggested that maybe the experiments were only catching a small, biased sample of the photons. They argued that if we could see every single photon, the classical model might still hold up. Modern experiments now use superconducting nanowire single photon detectors that are efficient enough to capture almost every particle. Even with this nearly perfect vision, the violations of classical logic persist. We are not looking at a small error or a lucky guess. We are looking at a fundamental property of nature that refuses to behave like a machine. Every time we improve our instruments, the gap between the classical story and the quantum reality grows wider and more undeniable. This brings us to the truly mind-bending concept of entanglement swapping. In a normal setup, you create two entangled photons from a single source. But in swapping, you take two independent pairs of photons that have never seen each other. You take one photon from the first pair and one from the second pair and perform a special measurement on them together. Suddenly, the two remaining photons, which are miles apart and have no shared history, become entangled. This is a massive shift in our understanding because it shows that entanglement is not just a link between particles that were born together, it is a web that can be woven across different systems. The mechanism here is a mediator measurement that forces the distant particles into a shared state. It is as if you could make two strangers become identical twins just by looking at their neighbors. Physicists have pushed this even further by creating entanglement between photons that do not even exist at the same time. They use a process where one photon is measured and destroyed before its partner is even created. By the time the second photon appears, the first one is already gone. Yet, when the data is compared, the two photons show the same impossible correlations, as if they were standing side by side. This destroys the idea that entanglement is a physical cord or a shared vibration. How can a link exist between a particle in the past and a particle in the future? The measurement of the first photon leaves a trace in a third particle, which is then used to bridge the gap. This proves that the universe does not view time as a one-way street where things must overlap to interact. The connection is outside of our standard timeline. This leads us to the strange world of indefinite causal order, tested through something called a quantum switch. In our daily lives, if you put on your socks and then your shoes, the order matters. You cannot do both at once in a different sequence. But in a quantum switch, a photon passes through two different processes, let us call them process A and process B. Through the power of superposition, the photon does not choose an order. It exists in a state where it has gone through A before B and B before A at the same time. When researchers measure the final state of the photon, they find interference patterns that could only exist if both sequences happened simultaneously. This is a direct challenge to the idea of a fixed causal chain. It means that on a fundamental level, before and after are not absolute truths, but depend on how the system is measured. To ensure these results are not being rigged by local factors on Earth, some physicists have turned to the stars. In the cosmic bell tests, researchers used light from distant quasars that are billions of light years away to determine their measurement settings. The idea was to ensure that no hidden variable on Earth could have influenced the experiment for billions of years. Even with the settings chosen by ancient light from opposite sides of the universe, the entangled photons still broke the Bell inequality. This measurement method pushes the stakes to a cosmic level. It suggests that the rules of quantum mechanics have been consistent across the entire history of the universe. It is not just a lab trick. It is the fundamental language of reality. We also have to consider the phenomenon of negative group delay. When a photon passes through a specific type of medium, like a cloud of cold atoms, the peak of its wave can appear to exit the medium before it is even finished entering. While this looks like the particle is moving faster than light, it is actually a complex interference effect where the front of the wave is reshaped. No actual information travels faster than light, but the timing is so counterintuitive that it breaks our classical sense of a particle traveling through a tunnel. This reinforces the idea that we cannot think of photons as little balls moving at a set speed. They are wave functions that can stretch and overlap in ways that defy simple visualization. This reality check reminds us that while the results are weird, they still respect the ultimate speed limit of the universe. One of the most famous ways to see this is through the Hong-Ou-Mandel effect. When two identical photons hit a beam splitter at the exact same time, they always leave together in the same direction. They never go separate ways. This provides a way to measure timing that is more precise than any physical clock. By looking at whether the photons bunch together, physicists can tell if they arrived within a quadrillionth of a second of each other. This level of precision is what allows us to verify that the timing of these quantum events is exactly what the theory predicts, even when those predictions seem impossible. We are not guessing about the timing, we are using the photons themselves as the most accurate stopwatches ever created. There is also the concept of the quantum eraser, which adds another layer of forensic intrigue. In this experiment, you can detect a photon and record which path it took, which normally destroys its ability to create an interference pattern. However, if you then erase that path information after the photon has already been detected, the interference pattern reappears in the data. This implies that the history of the particle is not set in stone, even after the event has happened. As long as the information about what happened can be hidden or revealed, the particle's behavior remains fluid. This changes our understanding of the past. From a solid record to a collection of possibilities that only settle when the final piece of information is locked in. Even with all this weirdness, there is a strict rule called the no signaling principle. You can have instant correlations across the galaxy, but you cannot use them to send a message. If you try to change your end of the entanglement to send a bit of data, the other person just sees random noise until you send them a classical signal at the speed of light to explain what you did. This is the ultimate information bottleneck. The universe allows for a deep, instant connection, but it forbids us from using that connection to break the speed of light for communication. This is a vital distinction because it prevents time paradoxes while still allowing the universe to be non-local. It is a delicate balance that keeps the laws of physics from collapsing into chaos. Another fascinating discovery is the monogamy of entanglement. A photon can only be perfectly entangled with one other system at a time. If it starts to become entangled with a third particle, its connection to the first one must weaken. This acts as a limit on how the spooky connection spreads. It tells us that entanglement is a specific, limited resource in the universe. It is not a magical glue that connects everything to everything else at once. It is a structured relationship that follows its own set of strict mathematical rules. This prevents the entire universe from becoming one big blurred mess and allows individual objects to exist with some level of independence. Now we must answer the title question directly. How did physicists time entangled photons to prove the classical story is wrong? The answer is the verdict provided by the data from the Bell tests, entanglement swapping, and the quantum switch. The evidence eliminates the old explanation that particles carry pre-written instructions or hidden scripts. It shows that the results are not the result of local signals traveling at or below the speed of light. The measurements leave no room for the idea that events must happen in a single, fixed, chronological order. The mechanism that is strongest is the quantum state itself, which exists as a probability wave that spans across space and time. What remains unresolved is the exact nature of the transition from this quantum blur to the solid, single timeline world we experience every day. The evidence proves that the classical handle on reality is broken because it cannot account for the correlations we see in particles that never coexisted or that exist in multiple orders at once. This verdict changes everything about how we understand the universe. It means that space is not a series of isolated points, but a deeply connected fabric where distance is an illusion for quantum information. It means that time is not a rigid arrow that dictates every interaction, but a flexible framework that can be bypassed by the right kind of measurement. When you look at the world now, you should see it not as a collection of separate objects, but as a vast interconnected system where the past and the future are more linked than we ever dared to imagine. The classical story of a clockwork universe is dead, replaced by a reality that is far more mysterious and magnificent. The forensic trail of these experiments leaves us with a sense of clarity about what is not true, even as it opens a door to a deeper mystery. We can be certain that the old model of local realism is insufficient to describe the world. We can see the patterns in the data, the precise timing of the photons, and the undeniable strength of the correlations. This is not a matter of belief. It is a matter of measurement. The universe is telling us that our common sense is a limited tool, built for survival on a human scale, but blind to the true nature of the cosmos. As we continue to probe the limits of quantum timing, we're not just learning about light. We are learning about the very foundations of existence. If you found this exploration of the quantum world valuable, consider following for more deep dives into the evidence that defines our universe.